protocol for communicating these factual and counterfactual explanations. And finally, he will outline the main challenges to be addressed as future work. His supervisors are Jose Maria Alonso, Alejandro Catala, and Martin Pereira Fariña. So, Ilia, go ahead, please.
Thank you. So, good morning, ladies and gentlemen. I would like to present this morning. I would like to present to you the ongoing work in my doctoral thesis entitled "Argumentative Counterfactual Explanation Generation." Conversational agents for explainable AI. So in this talk, I would like to first introduce you to the topic of factual and counterfactual explanation by first motivating the need for explanation in artificial intelligence, then describing the properties of what is considered to be good explanation and what explanations are considered to be good enough or explanatory enough. Then finally, I will present to you the concepts of factual and counterfactual explanation as defined in the literature. Then I will move on to presenting to you some of my previous work here at CiTIUS when we worked on explanation generation methods for interpretable models, such as decision trees, and some APAC models, some of which include fuzzy rule-based classification systems. Then I will move on to give a very brief overview on of the current work that I'm involved in and some future work, so immediate future work that is to be done while finalizing the work on the doctoral project, which includes human evaluation of counterfactual explanations and explanatory dialogue modeling. And then I will conclude with outlining some open issues and challenges and the topic in the area of counterfactual explanation generation. So I do not think it is worth spending much time on motivating the need for explainable AI. I would just like to briefly mention the very main reasons to why we need to make AI explainable. So first, evidently, explanations serve to justify predictions of various AI algorithms or intelligent systems based on those AI algorithms, so that they enable us to verify the given automatic decision. Then these explanations, these automatically generated explanations, also help us to identify correct errors or to debug the code that was previously written for those intelligent systems. Then these explanations, these automatically generated explanations, also allow us to iteratively improve the previously built systems as a result of human-machine interaction as well. And finally, explanations allow us to discover new facts, to learn new facts, to infer new knowledge from what could have been hidden from us in the first place. So what explanation? What is actually explanation, and what is considered to be good explanation? From social sciences, we know, and social sciences, humanities give us quite a lot of insights on what explanation is. Well, in fact, the concept of explanation has been long studied, and I think it roots back to ancient philosophy. So in modern social sciences, explanations are claimed to be contrastive, selected, and social, which means that people do not necessarily ask why some event P happened, but rather why that event happened instead of some other event Q. In the context of artificial intelligence, we could draw to the fact that some AI algorithm predicted, it gave out a certain prediction P, and then it is also required that we explain why some alternative non-occurring predictions did not take place, why they were not predicted. To which we refer as those events Q. Then explanations they should be selected, which means that they must only include a limited number of causes that constitute the actual explanation. In fact, we're not really interested in knowing all the possible causes that that could motivate the actual prediction of the algorithm, but only the most relevant of those causes. And finally, explanations is also viewed as a social process, which is defined as a transfer of knowledge presented as part of the conversation or interaction, and are thus related to the explainer beliefs, but the explanee belief, which means that the explanation is dynamic. It is constructed in an interactive process where at least two agents are involved. Well, the explainer and the explanee, the one who generates the explanation and the one who is a recipient of that explanation. So, given these properties of the explanation, which can also be seen as requirements to what an explanation should be, we can define the main objectives, which is to design, implement, and validate an explanation generation framework, which satisfies the aforementioned requirements to explanation. So that said, we've got three sub-objectives. We first have to make the explanations contrastive, then make sure that they are also selected, and finally social. And this is throughout this talk, I'll be moving through these three subtopics accordingly. So as for the task, we're given some data set X, which entails a set of classes Y and a classifier C. So eventually, we solve the the general classification problem. So we do not only classify some instance, but rather explain why the classification of some given instance X was performed in the way it was done, and not in any other way. To do so, we consider two types of explanations. Those are factual explanations, or factuals for short, which provide a set of causes that led to the actual prediction. For example, this can be illustrated with an example from the financial domain, where the loan application can be rejected because the applicant's income was too low, or the number of actual loans that the applicant already has got is too high, or for example, is more than 2 in this case. At the same time, it is possible to also explain why some other outputs were not predicted. In this case, what should be done so that the loan application would have been approved. To do so, we suggest a minimal change in feature values so that the classifier's decision changes. In this case, we state that the loan application would have been approved if the monthly income were at least 5,000 euros. So both types of these explanations, they allow us to construct a reasonably fair big picture of the reasoning of the underlying reasoning behind the algorithm that made a prediction, which was by default not explained at all. So moving on, we define these explanations formally as follows. So explanation is viewed as a piece of text justifying the actual prediction, as well as, just one second, as well as a possibly empty set of non-predictable alternatives. Again, that depends on what we can actually extract from the classifier and how we can solve this. The problem of generating these counterfactuals. So we see them as a union of one single instance of the factual explanation, given that no alternatives to that factual explanation exist, and a set of counterfactual explanations for each of the counterfactual classes. So for each of the classes that were not predicted. We use the following basic general textual templates for each of the types of explanations. So for factual explanation, the test instance is of class y1 because some feature 1 takes on the value 1 v1, and some feature f2 takes on some value f2, and possibly something else. Then counterfactual explanation would describe a set of features feature value pairs that would lead to a change in the prediction, which would lead to another prediction. And obviously, well, as I just said, we do not only work on generating explanation, the counterfactual explanation for one single given class, counterfactual class, but rather for all the other non-occurring alternatives. Then it turns out that the state-of-the-art methods for generating contrastive as well as counterfactual explanations encompasses a lot of problems that do not allow direct synthesis between the theoretical frameworks that have been proposed for a long time with the actual computational frameworks that have been used ever since this problem has emerged in the context of explainable AI. There is, in fact, quite a lot of mismatch in terms of the terminology applied to the concepts of contrastive explanation as a property of explanation to give out the comparison with a different class, and the counterfactual explanation, which must obviously suggest that minimal change. So in this sense, we can view the counterfactual explanations as some sort of a subclass of explanation, which is encompassed by a bigger concept of contrastive explanation. So in fact, theoretical frameworks are mainly rooted on the concept of causality, in which we do come across quite a few various classifications thereof, which is not often the case with respect to the state-of-the-art computational frameworks for their generation. Nevertheless, we can emphasize the strong need for having such types of explanation generated as they appear in various artificial intelligence problems, such as not only classification, which is naturally the case, but also regression, knowledge engineering, automatic planning, even recommendation running and conflict resolution. The frameworks of the counterfactual explanations are used in different settings. Those could be model-specific methods where we have the access to the internals of the model, or model-agnostic methods which actually treat black boxes without having any direct access to the features, so that they do not generate any feature-based explanations like those that were mentioned in the previously. As for the output representation, again, we come across a variety of types of output representations in which the counterfactual explanations are generated. So, for example, those could be, again, feature-based or interval-based explanations which are basically used when we do have access to the internals of the model, or those could be purely textual descriptions, or visual descriptions as well, or even multimodal types of explanations as well, which combine some or all of the aforementioned types of output representation. And finally, there is a great challenge with evaluating counterfactual explanations, because when we deal with non-occurring alternatives, we actually hypothesize some scenarios that did not even take place. So then the question arises: how can we actually prove that what did not take place in reality is true at all? Which leads us to a further distinction between the metrics and methods used for evaluation of counterfactuals. Again, just to introduce a few basic metrics that are currently used. Among others, those can be subdivided into automatic quantitative metrics and human evaluation metrics. So for automatic metrics, we tend to distinguish between validity, which is the fraction of examples returned by the method that are actually counterfactuals. That is to say, given some counterfactual examples and given some explanations for those examples, not necessarily all of them, they lead to the desired outcome, to the alternative desired outcome. So we first, of course, need to verify which of them are true counterfactuals. Then we also tend to evaluate them in terms of proximity, which is the mean of the feature-wise distances between that counterfactual example and the original input. Then counterfactuals are encouraged to be sparse, which resembles the number of changes between the original input and the generated counterfactual, which means that it is more favorable to have less changeable features, which are more significant in terms of the distinction between the original input and that different classification that we obtain in the end, rather than having a change in many features which differ less significantly in comparison to the original input. And then finally, counterfactuals are encouraged to be diverse, which resembles the mean of the distances between each pair of examples, so that the original input and the counterfactual output are as representative as possible. However, these are not the only metrics of evaluation metrics of counterfactual, because it is also important to note that, for example, counterfactuals must be actionable, which means that we shall not be able to change the feature that cannot be modified at all. For example, age. We cannot really tell the user of any application to become younger to point in order to get their living application approved, right? So this would just not be actionable at all. So then, what is much less explored and yet quite actively investigated is human evaluation metrics, because in the end, well, as we move on to human-centric AI, what we in fact need to take care of is how such explanations are perceived by the end users, and how trustworthy, how satisfactory they are from the user's point of view. So, to give you a very brief overview of how of the brief challenges of the main challenges that are tackled in this doctoral project. I'm just going to show you this the scheme of the classification. Problem: imagine we have a few, well, in this case 4 classes that our data set comprises. So the prediction given out by the classifier is class Y, or solution 1. We may have only one factual explanation, which is sometimes the case, which can be sometimes reconstructed from interpretable models, or there may exist various factual explanations as well. We will have to find a way to treat those as well. Then we have several counterfactual classes which were not predicted by the classifiers. So while following the formal definition of the explanation as was defined in the previous slides, we treat them as a union of the most relevant explanation to the original input for the given test instance. Then imagine we could simply come up with a collection of such explanations. We could rank them. We could estimate their relevance to the original input. However, the end user may not really be satisfied with what such a system gives out to them, just because they may find other explanations other pieces of explanations more relevant than those presented to him or her. For example, the end user may still be satisfied with the factual explanation, but if the system automatically estimates and generates the most relevant explanation for class Y prime, for example, to be CF explanation 1, it may be the case that if the end user were presented counterfactual explanation ranked 3rd by relevance for that class, that user might be way more satisfied with it than than in the actual case where the system just gives out the most relevant explanation to them. The same applies to class Y double prime. And then finally, for some other class Y triple prime, the end user may not want to need any explanation, any counterfactual explanation at all. And well, we still have to find a way to customize, to personalize the given explanations in this manner. So then the explanation must be adapted to the user's needs, right? So this leads us to a few methodological challenges as reviewed in this introduction. So first, we need to figure out how to generate potential candidate factual and counterfactual explanations. Then we need to find a way to rank those candidate explanations by relevance, by their proximity, for example, to the original input, or by their proximity to the decision boundary. Or in any other way, and then finally we need to find a way to personalize the generated explanations. So all of these challenges are connected, are directly connected, directly related to the properties of good explanations that I mentioned before. And well, we try to, in this doctoral process, we try to come up with a general solution, with a generic solution for to tackle all of these challenges for a specific set of classifiers. So I'm going to, from now on, I'm going to use some examples using this using the beer data set, which is which contains only 400 data instances, which is illustrative enough to give out those examples, I guess. First, it is constructed, it is annotated by the expert brewer. So the piece of knowledge that it contains, it is reliable in the sense. Then it serves the problem of multi-class classification. So as is not always the case, as you know. Where we only deal with, for example, two classes. Well, it is much easier to reconstruct a bigger picture of the classifier's reasoning when more classes and more alternatives are present in the data set. So the data set is well balanced. Each of the classes contains only 15 instances per class, and it contains only 3 features: color bitterness and strength. Each of the features are associated with a set of linguistic terms, each of which are described or defined, are mapped to an interval, to a range of values associated to them. And all the features are they are measured in terms of internationally recognized, acknowledged scales for color, bitterness, and strength. Then again, all those are mapped to trapezoidal functions that we will later use for generating explanations for some fuzzy release classifiers. And then finally, we also consider, well, in some of the experiments that I'm probably not going to mention in this during this talk, in some of the experiments we also will try to attempt the challenge of using trapezoidal functions that comprise adjacent linguistic terms. For example, as in this case, for example, the shaded region in yellow comprises the trapezoidal functions for color being straw or amber. So just to give you an example, so we started off with generating counterfactual, with factual and counterfactual explanations for decision trees. Decision trees are in fact interpretable models. So it is not, I mean, it can be seen trivial that to reconstruct a factual explanation simply means to aggregate the explanations that we get from the internal nodes of the tree that constitute the decision path to the actual explanation. In this sense, despite the fact that this is not the only way to construct a factual explanation, and despite the fact that it does have certain drawbacks as well, what is much more interesting in this case is how to properly constitute or generate a counterfactual explanation. For example, for some class 5, as you can see, it does not only has to be the closest node. Oh, well, the closest decision path leading to the closest decision path with respect to the one leading to the actual prediction, but also we need to tackle the problem of having multiple counterfactual explanations, because it may be the case that the farthest, even if some decision path or some leaf node that is located further away from the actual classifications node, it may still have more representative features for the minimal change to be suggested to the end user for that counterfactual explanation, rather than the decision path that is supposedly closer to the factual explanation path. So to do so, well, we decided a pipeline where we first where we have two pieces of data for input. So we have a collection of decision trees, or well, in this case, just to simplify things to facilitate understanding behind the method. Let's just take a single individual tree as an example, and some given test instance. So we first generate the candidate counterfactual explanation collection. In order to do so, we construct a rule matrix where the rows are in fact all the decision paths that we encounter in that decision tree. Then we've got a number of internal conditions. Then we've got a set of internal conditions, all the unique internal conditions that we can find in the tree that considers the column of the matrix. Then we measure the relevance of this decision path in accordance with some given distance. In this case, in the first bunch of examples, in the first bunch of experiments, the XOR-based distance was used. The underlying intuition was to tackle the main differences, the differing bits between the nodes that actually make up the decision path, the factual decision path, or any counterfactual decision paths, and all the others. Then we rank those decision paths by relevance, and what we get in the end, well, we aggregate all those feature values among the most relevant decision path for each class, and then what we get is a decision path that supposedly leads us to always valid counterfactuals, so that we can be sure of the fact that any change introduced by the end user will always lead to the actual desired outcome. I'm afraid that I have to be moving quite rapidly, because I still have quite a lot of stuff to present. So I'm going to speed up. So as for the first preliminary results obtained like 1.5 years ago, we simply measured we simply evaluated the counterfactuals in terms of the best minimal distance from the factual decision path to each of the counterfactuals. So you can see as the tree is becoming more complex, then the best minimal distance to those explanations increases, which means that the relevance of such explanations increases as well. Then, however, this method has several limitations. Well, first, obviously, since we deal with binary values and binary vectors, since only a few nodes in the decision tree are present in each of the rows of that matrix, the matrix results to be highly sparse, then explanations may include too many features still, which would violate the requirement to the explanation being selected. Especially due to the fact that some of them may be irrelevant or poorly explanatory. Well, in this use case, we only have 3 features, but imagine what would happen if we had like hundreds of them. In fact, in a complex enough decision tree, we might end up with having hundreds of features in the final explanation as well. Then the test instance vector is binarized. So the same method was applied to fuzzy decision trees. Where we observed a lot of information loss, because we obviously by binarizing those real matrix values, we do lose a lot of information on how certain the classifier is with respect to some alternative outcomes, non-predicted outcomes. Then finally, several counterfactuals may have the same distance because as we normalize by the number of the unique conditions and the real metrics, we end up with having a highly strict, strictly limited number of potential values that the distance itself can take on. So eventually, well, the method was to be extended so that feature value relations could be captured better in order to avoid information loss. So let us then move on to the case of fuzzy rule-based classification systems. Well, here's an example of the actual rule-based that was used as an alternative to the explanation and to the decision tree classifiers. In this case, we do have in this case all the linguistic terms are present. I mean they are interpretable again. So we could in theory apply the same method to just generate the explanations, well, both factuals and counterfactuals in this case. But as it will turn out later, as it will appear later, this would not be that would not be sufficient to generate explanations for the same fuzzy rule-based classifications based on attack rule learning algorithms. So in order to extend the method, we consider the same rule matrix, but now we introduce the Euclidean distance, where we represent each vector, each rule as a vector in an m-dimensional space, where m is the number of all the node rules for the decision tree, or possible feature values for the rules actually for the fuzzy rule-based classification system. Then each vector represents a consistent collection of propositions. Then we apply these two different distances to see whether we can actually overcome the challenge of losing any information that could be relevant, that could actually lead to using it, which could actually increase the quality of the output explanation. Then, well, the final objective is to minimize the distance between the factual explanation or the test instance vector and the candidate counterfactual. And then finally, for some attack models, which I will very briefly show you later, we need to apply linguistic approximation, as those linguistic terms are never semantically grounded by default. So to very briefly mention how the experiments were designed, in this case, well, consider the same binary test instance vector and the binarized real matrix based on the use of a XOR distance for generating counterfactuals for experiment 1, and then for experiment 2 for using as we use fuzzy rule-based classification systems, we do not. Well, first we represent the test instance vector as a vector of membership function values for the given test instance. We do not binarize it anymore. And we apply a different distance of the Euclidean distance in order to see whether it can capture the specific properties that the fuzzy rule-based classification system can give us to. So then again, the candidate counterfactuals were ranked by relevance. Then in the case, in the case of dealing with opaque models, which I will show you briefly later, we need to apply the approximation layer, where we simply apply a series of thresholds, a series of cutoffs, sorry, with a small enough step, so that we could then apply major voting to define the actual linguistic term for the output explanation. Then as soon as the most relevant and the best approximated counterfactual is selected, we can then pass them on to the natural language generation module. I will probably have to skip the examples again. And just to very briefly mention it to you here, and this slide, you can see that factual explanations for fuzzy rule-based classification systems do not only presume one single instance. In fact, in this case, we've got, for this particular test instance, we've got two rules fired, two rules activated, which would lead us to two different factual explanations already at this point. So in this case, we simply pick up the one that activated with the most, well, with the highest activating degree. However, the explanation which would probably have a more representative and more, well, a better explanatory properties is the combination of the two, with explicitly mentioning which one, which of the two has a stronger, well, a higher activation degree, and which is, and the other one being, well, the system being not so confident in. Again, as for the XOR method, as you can see in this case, for when the linguistic terms are given and are well defined, we can only have 13 potential combinations, which we could then rank in accordance with the given distance metric. However, things change when we apply the Euclidean distance. It turns out that that as we apply two different methods, the output explanations for the same classifier for the same model can actually differ. So we would then have to state that the desired outcome, that the counterfactual outcome would have changed if you changed a set of two features in the former case, in the case of following Rule 13, otherwise. Or changing another set of features to another set of values. In the case, well, if the counterfactual explanation generation module selected Rule 14 to be the most relevant to the original input, then another problem comes up with when we have to deal with a pack model is a pack fuzzy rule-based classification models, which is represented by the case of the FURIA algorithm. Where each rule in the rule base represents a trapezoidal function with the pre-learned trapezoidal functions which do not preserve any semantically grounded meaning. So we cannot really say what term each of the features should be mapped to or should be associated with. So then, in this case, what we need to do afterwards, after the most relevant counterfactual rule is selected, is to apply linguistic approximation, where we map each of the we're given some threshold value sigma 1. We apply the similarity measure between the interval in which each of the linguistic terms is defined to the actual interval that this given feature represented by this trapezoidal function is defined across. Then it turns out that the use of the Euclidean distance allows us to better capture some fuzzy-specific properties of that such classifiers provide us with. Naturally, the use of Euclidean distance allows us to operate on a membership function value without having to avoid any information for that. So instead of binary ranking the membership function value vector and then applying some heuristics, we could then directly represent them in some n-dimensional spaces, potential vectors, and then apply this distance measures directly to those. So it does guarantee no information loss due to which is caused by binarization, as in the case of crisp precision trees, that appears more sensitive to changes in membership functions. We note that we do not really have to care about the actual values that the Euclidean distance provides us with, because in the end what we need is to simply rank those output rule representations. So we do not really have to normalize them in the end, even if we have to compare it with some other metrics that do allow us to do that. For example, the use of cosine similarity for measuring relevance was not applicable because several rules applying it to several counterfactual rules would result in division by zero, because some of the features of feature values would always result with zero vectors. And then finally, the use of Euclidean distance also allows us to better illustrate the diversity of candidate counterfactuals. As for evaluation, well, again, since human evaluation is underrepresented in the existing body of literature, we came up with a couple of surveys to actually evaluate aspects of those competing factual and counterfactual explanations. So first, we applied a set of well, we designed a set of aspects of explanations that could be theoretically grounded. In this case, they are linked to GUAJE's maxims. In the former case, in the first case, so this is a set of maxims that that allows us to that is well known in computational semantics and pragmatics, that allow us to estimate the informativeness of any given text or dialogue. In this case, explanation. So we can then measure informativeness of those explanations, accuracy of those explanations, not from the system's point of view, not from the system's perspective, but rather from the user's point of view. Then their relevance, again, and then we could measure the relevant. Now that we have already come up and decided the metric of measuring relevance of explanations that comes out directly from the model as an objective metric, as an automatic metric, we can then compare it with the relevance as measured by the end user, so that we can challenge. We can challenge the two interpretations of what relevance actually is. And then finally, what is of course important is to also measure the grammaticality of those explanations. Then finally, since that survey was complex, it was probably too complex for an average user to evaluate, because it probably contained too many tasks to do. We came up with a simplified version of that where we simply measured trustworthiness and satisfaction for those generated explanations. I'm pretty sure that some of you have already participated in the survey, and I would like to thank you for that. However, well, the second version of the survey is still running. This one, as I told you, this one is it has been simplified a lot. So again, well, we stick to this.
Ilia, please, can you speed up for the time?
Sure.
I think we are running out of time.
Yes, sir. I would nevertheless encourage you to participate in the survey while it's still open. Well, your feedback would be highly appreciated as well. You can find this link later on and follow it later. So then finally, now to the third and the final aspect of the explanation that needs to be represented as well, as the explanation must be modeled to be social. We assume that the explanation is formed dynamically in a dialogue with the system, so that we can personalize it really. And in this case, well, the user him or herself decides what is to be requested to be explained. This can be formed in a dialogic interaction. So that the end user may want to argue over the given piece of explanation to fine-tune it. So given this collection of counterfactual explanations, the candidate counterfactual explanations, it is now the end user who can actually argue for probably not necessarily the most relevant one, but another piece of explanation. And again, this would allow us to construct not only to construct a formal framework for communicating such explanations, but also to compare the results that we have collected by measuring, by estimating, by evaluating those counterfactuals using an objective automatic metrics, but with those collected from the end user. So then what we use is a dialogue game. It's an argumentation-based method of formal dialogue modeling based on the speech-act theory, where while in general, in the argumentation theory, some premises, which in this case are feature value pairs, are to be attacked in order to verify if the claim, which in this case is the prediction of the classifier, is to be attacked. So the premises are attacked, and if you are attacked well enough, then the claim is to be rejected. We could apply the same scheme to the counterfactual explanations. What we cannot do is to actually attack them in this trivial way, because, well, we cannot really attack the ground truth data, because we know that the premises are always true in this case. So what we do instead is that we introduce this intermediate explanation layer and we attack those explanations instead. So I'm probably not going to describe all the formal properties of the dialog protocol, but well, just to summarize a few request types. It was found necessary to model at least the four mentioned in this slide. So whatever we can get whatever we can get from the interaction with the end user, and whatever we can get from the classifier too. So we first need to model the explain request. Then we need the end user to allow the end user to ask for digitalization for some specific request for some specific explanation. We then need to enable them to be able to clarify something, whatever is left unclear in the explanation. And then finally, in order to model not only information seeking but also persuasive dialogue, we need to enable them to argue with the system, outputting those explanations. Formally we define a dialogue as a tuple which contains a set of dialogue participants, in this case only two, the system and the user. The dialogue is comprised of a set of dialogue moves that the players make in the course of the dialogue. Obviously, the dialogue protocol contains a set of rules that govern the flow of the conversation. Then, in order to personalize that explanation, exactly to keep track of the explanation presented to the end user, as well as the final explanation generated at the end of the dialogue, we need to keep the explanation store. Then the details and clarification stores keep track of what has been presented and what has already been detailed or clarified to the end user. And then finally, of course, what we need is to make use of the system's knowledge base and some dictionary that contains the necessary features or actions, the clarifications of those. As an example of an explanatory dialogue, you can see in this example that this dialogue has a hierarchical structure, highly hierarchical structure, which is governed by the initial claim of the system makes, where it simply describes the actual prediction. Then, as for the user may want to exercise the right to explanation or not, or jump straight to conclusion if they are satisfied with the original claim. As for the explanation, we may want to offer to the end user some piece of factual explanation, which could then be digitalized or clarified or argued against. The same applies to counterfactual explanations for any counterfactual class, so that the explanation store keeps track of all the explanations that the end user commits him or herself to, so that the final set of pieces of explanations that we get in the concluding mood of the dialogue represents exactly those that the end user is actually interested in, instead of just outputting them all the one-shot explanations that we could ever get automatically for all the counterfactual classes. As you can then see, this dialogue, while having a highly hierarchical structure. Sorry?
Ilia, could you conclude? If not, we will not have time for questions.
Yeah, I only have a couple of more slides to add. Since the explanatory dialogue has a hierarchical structure, it can be modeled in the following way. So we can make use, as you can see, we make use of the speech acts as defined in accordance with the dialogue protocol. So that any explanatory dialogue that is modeled in accordance with the given dialogue protocol can be parsed, and so if it is defined properly, it will always make part of the formalism that supports the dialogue, which is in this case defined as a context-free grammar. Which I will probably not go through. And so as part of the future work, so we're first, as for future work, we need to finalize collecting the human evaluation results and report them, which is quite an urgent issue. And then finally, as for the explanatory dialogue, well, as you can see, if we take a look at the original pipeline of the dialogue systems, the dialogue manager that you can see to the right-hand side of the picture in this slide has already been modeled. The LG model is also there too. What is really needed is that first this dialogue protocol needs to be properly validated. Then the natural language understanding module needs to be introduced as well, so that the end user does not only operate, or would not only operate on the predefined moves, but so that their intents can be recognized properly. So then After validation, this download chronicle could be extended if necessary, and then finally, well, the final product, the final conversation legends would then be validated and adapted against the baseline dialog system. There obviously there are lots of other issues and challenges that embrace this wide area of factual and counterfactual generation from them. Those in green have, at least in part, been addressed as part of this doctoral project, but of course a lot more remains there. One of which, and well, perhaps one of the most important and one of the most widely discussed subtopics in this area is, of course, causal inference and, well, the causal attribution of those features to the actual output explanations. Well, that's that. I think, yeah, that's it. Yeah, thank you for your attention. If you have any questions, well, I'm happy to answer them.
Thank you very much, Ilia. Sorry for interrupting you, but we wanted to have some time for exchange. You had so many interesting things to show that the time was very short. So are there any questions for Ilia, please? Yeah, Felix, I think he wants to say something.
Okay. Okay, thank you, Ilia. Okay, the presentation, it was too difficult for me for follow it, but okay, I think I picked a general idea. I think that is a very interesting topic to work. I have a question because I am not sure, but when you are developing all these systems for counterfactual explanations, in some way you are assuming that your data is a good representation of the world. I mean, for example, sometimes if you're thinking a counterfactual explanation, is possible that, okay, your data don't represent that perhaps you don't have the data to answer the question, or you can have some kind of bias. I don't know if you understand me, what I mean, but I mean, how you could know that your data is good enough to give an answer to a counterfactual question that is in an open world and it could be not represented in your data.
Yes, of course. Well, that's one of the greatest challenges as well. I mean, well, in the end, well, the data that we've got, the data we have is, well, is what we have. We have to work with the data we've got. But well, there exist alternative methods that, well, that make use of interpolative models as well. I mean, we do not really, especially in the case where we do not really have access to the internals of the model, we cannot really construct feature-based explanations as well as in this case. But instead, we focus on the areas of the areas that are close enough to the decision boundary between different classes, and then if the actual data, the training data is not good enough, if we know that it's not good enough, what we can do alternatively is to actually synthesize a local neighborhood of data points around the decision boundary, and then build up an interpretable model on top of that data. Well, using that data.
Okay, I think I follow you. Okay, thank you. Okay, perhaps I could ask you someday, okay, after this doctoral meeting. Okay, thank you.
Thank you, Felix. So, Luca, do you have some questions?
Yeah. So first of all, thank you, Ilia, because it was really interesting and insightful. And yeah, we don't have like much time, but also like I'd like to focus more on the idea of the metrics you were following, because I've seen you were exposing like Paul Grice maxims, and maybe I followed the point, like, but how would you convert these kind of maxims that are related to pragmatics to like different, let's say, features that are not just within the system? Like, for example, I think about like different users with different, application domains and different requests of explanations. How would you translate that? Like,
do I get you right if I say that your question is about is about translating. Is not about selecting the method that we use to estimate the values that we can get from the end user, but rather the use of such metrics across various applications.
Okay. Yeah.
Well, yeah. I mean, if I get it right, well then, well. In fact, what is used in this case, well, is just well, one general method that is used to evaluate these human ranks, or just, well, Likert scale based data. So that we can what we can do is to have those methods, or well, the output explanations ranked again by the end users themselves, and compare the rankings themselves, the rankings as constructed by a bunch of end users against the rankings, the set of counterfactuals ranked by those automatic explanation generation algorithms. So if we compare these ranks, we would probably never be mistaken, never be wrong, judging which of the methods performs better, gives out, well, better explanations, or explanations that that pertain more, well, quality in the end.
Oh, okay. So like, if I get it right, like to sum up, it's a kind of self-assessment, like a comparative self-assessment of the expectation, like satisfaction of the end users compared to the output generated. Okay.
Precisely.
Yeah. I look forward to continue this conversation privately. Yeah. Thank you. Thank you again.
Thank you. Sure.
Okay. Some more questions? No, it seems that there are no more questions, so I think that we can stop there. So thank you very much for your presentation, Ilia.
Thank you.
Very interesting PhD. Challenging also, doing all these explainable techniques in order to understand better AI decisions. Good luck with the continuation of your PhD and your research.
Thank you so much.
Thank you
to the audience. See you.
everybody. Bye-bye.
Bye.
Thank you. Thank you, everyone.